Welcome back. Today we're going to look at series and parallel combinations of resistors and also look at them for voltage sources and current sources as well. We saw how to combine series resistors in an earlier discussion where the resistors just add, and then we also saw how to combine resistors that are connected in parallel, the reciprocal, the sum of the reciprocals. So today we're going to look at taking resistors and have them both in series and parallel all mixed up and then find an equivalent resistance. So let's just dive in. That's the best way, I think. So what we're looking for is we're looking for an equivalent resistor. So I'm looking for the single resistor, Req, that is going to be equivalent to the circuit. And by equivalent, remember what we mean by that. We mean that if I were to put a voltage V right here, that's going to give rise to some current because of the fact that you got a conducting path from the higher energy level to the lower energy level. Well, if I were to put the same voltage here, I want the same current I to flow. And if I can find this resistor that will have the same VI relationship as this circuit, then I have the equivalent resistance. That is, the two circuits will behave the same from a VI point of view. So how do we do this? Well, the best way to do this, I think, is to get a set of colored pencils and then just start coloring the nodes, and that makes things a little bit more apparent. So we'll get a colored pencil, and then we will just color all of this node. Everything along this wire is the same energy level, so it's the same node, so we'll make it orange. Then take a different color, and just start over here, and you just color the wires until you hit a circuit element. When you hit a circuit element, on the other side of the circuit element is in general going to be a different energy level, and that's going to be a different node. So just go through the circuit, coloring all the nodes, and so you can tell them all apart. And once we get the colors, all the nodes identified by color, then it gets a little bit easier to see what's going on. So here we go, we've got all the nodes colored, and so we're looking for parallel combinations. A parallel combination is going to be circuit elements that have the same two colors on their two ends, and we don't really see any like that right away. So now let's look for paths where a current will go through one element after the other, and we do see that. We see that any current that were to flow through the 17 ohm resistor would have to turn the corner and go this direction. So any charges that flow through the 17 ohms must also then flow through the 6 ohms, which then must also flow through the 7 ohm resistor, and that is the definition of series. They have the same current in them. And of course the equivalent resistance of 17 in series with 6 in series with 7 is just 17 plus 6 plus 7, and that's going to be 30 ohms. So I can take the 17, the 6, and the 7 ohm resistors, and I can replace them with a single 30 ohm resistor. And we have this circuit. So then when you get our colored pencils back out, and this is the orange node, and on the other side of the 8 ohm resistor is the yellow node, and then we see from originally that this is the purple. Now I'm being very careful to make all of these nodes the exact same colors they were before so I can compare these two. And so this is what we have. And if we look at this circuit, we see that the 15 ohm resistor has kind of yellow and pink on its two sides, and the 30 has yellow and pink. And what that means is that a voltage, which would be the yellow voltage to the pink voltage, could be called V, and then we see that the 15 ohm resistor has to have the same voltage across it as the 30 ohm resistor, and then two elements with the same voltage are in parallel. And the equivalent resistance of 15 parallel 30 is the reciprocal of the sum of the reciprocals. And to simplify that, you get one that's 2 over 30, and that's 1 over 30. And we find that's going to be 30 over 3, which is 10 ohms. So I can replace the 15 ohm parallel 30 ohm combination with a single 10 ohm resistor. In which case we have this circuit. So get our colored pencils back out again, and let's go on the other side of the 8 ohm resistor is yellow, and then this node there is kind of the pink. And if we look at this, we can see these are quite clearly going to be in series because any current that flows must go that way. And so the 8 series 10 combination will be an 18 ohm resistor, and so I can represent this with a single 18 ohm resistor, which leads us back to the circuit we started with, which is I now know that I can have an equivalent resistor which is going to be 18 ohms. And so any VI characteristic, any voltage I put there which gives rise to a current, will have the same VI characteristic if I'm using an 18 ohm resistor. So this 18 ohm resistor is equivalent to this network. Let's do another one. So this is a little bit different form. So let's start off by getting our markers out. And so the first thing we do is just start coloring our nodes to make sure that we can identify them all. And so we just start coloring them until we hit a circuit element. When we hit a circuit element, we change colors. And now we can take a look and see what's going on. And so we look for resistors that have the same two colors on both sides, and don't really see any of those. So then we start looking for series connections, and that is we're looking for circuit elements where the charges will flow one into the next. And we see right here that any current that flows through the 30 ohm resistor will have to turn and go through the 20 ohm resistor. So these two are in series, and then the series combination of 30 and 20 is simply going to be 50. So I can replace these two resistors with a single 50 ohm resistor, and the circuit will behave the same way. So we've got to get our colors back out. And it's really helpful when you do these equivalent resistor problems to redraw the circuit and recolor it each time. It really makes it, as the circuits get more complicated, it becomes more and more important. So now we look at these combinations, and then we see, just looking around, we see that if the 200 ohm resistor and the 50 ohm resistor have green and yellow on both sides, which means there's a voltage green to yellow which exists across both of them, which means we have 200 is in parallel with 50. And again, it's the reciprocal of the sum of the reciprocals. And when you do this, you get 1 over, and that'll be 1 over 200, and this is 4 over 200, and that's going to be 200 over 5, and that'd be 40 ohms. And so we see that the 50-200 combination will be 40 ohms. So redrawing the circuit, putting that equivalent resistor in, and we get our markers back out one more time and color everything in, and then we look and see what we have, and we don't see any parallels, we don't see any elements that have the same color pairs, but then I do see that any current that flows through the 20 ohm resistor is also going to flow through the 40 ohm resistor. So this pair there can be represented by the single resistor, which is 60 ohms. So I replace these two resistors with a 60 ohm resistor. And now it's getting hopefully more apparent what's happening as the circuit gets simpler. But we're still going to color it in just to make sure, keep our habits. And so if we look at this circuit, we see that the 30 and the 60 both have the same kind of pink yellow on both sides, so they must be in parallel. So we have 30, which is in parallel with 60, and 30 parallel 60 is the reciprocal of the sum of the reciprocals, and 30 parallel 60 is going to be 20 ohms, and so I can replace the 30-60 parallel combination with a single 20 ohm resistor, in which case we have this, and obviously any current that flows through the 5 ohms must also flow through the 20, and so we get the result that the circuit that we started with can be represented by a single resistor, and they will have the exact same behavior if that single resistor has a value of 25 ohms. Well, let's go to this bridge-looking circuit. This is a circuit that occurs fairly often, and so let's kind of look at it. And so in this particular circuit, what we're going to do is we're going to take a wire, and we're going to wire between C and D, and then we want to find the resistance looking into the A-B terminals. What is the resistance seen between A and B? So this is where your colored markers become really handy. So get your colored marker out and then start coloring. And this hopefully will help you see what's going on. This helps me a great deal, especially as the circuits get complicated or when they're drawn in kind of funny ways where it's not so apparent. And that's all one wire there. And so we see when we draw this, we have 3 different nodes in the circuit. And so if you want to then redraw the circuit, below we can do this. Here's the A, and so as we progress through the orange element, as we progress to the orange node, we see there's a resistor from the orange to the pink. So this is the orange node, and then there is a pink node, and there's a 12 ohm resistance from orange to pink. And we also see that there is also from orange to pink is a 6 ohm resistor. And so just as you keep filling in, you just keep making sure the colors line up. And then we see that from the pink to the yellow, there's also 12 ohms, and from the pink to the yellow is also 6 ohms. And that takes us back to where we started from, and that is B. And so this is the same circuit been redrawn, and it's a little more apparent what's going on now. So we see that from A to B, we have orange and pink, so there's a voltage across these two guys. So 12 and 6 are in parallel. We'll call that V1. And then this is pink to yellow, a voltage there. They're going to be V2. So we have 12 parallel 6 for the V1, 12 parallel 6, and that's going to be 4 ohms. And then we also have 12 parallel 6 beneath. That's also going to be 4 ohms. And if you want to put your colors back on to make sure you're still with me, here are the colors. And then at this point we can look and see that any current that flows this way must also flow that direction. And then we arrive at our result. There is an equivalent resistor. It acts the exact same way, and it's going to be 8 ohms. That's 4 series 4. Let's take that same circuit. Let's do it again. Let's look at, this time, leaving the circuit exactly as is, and let's find the resistance RCD. What is the resistance seen between these 2 points, the CD nodes? And so get your colored pencils back out. And so we're going to start at C and make our way around, and we can't go any further. And then we'll start at D and go, and we can't go any further. And then at this point, we see that this is a node, and that doesn't go anywhere, okay? And then we need one more color. And we see we have 4 different nodes. So if you want to transfer that, we're starting at an orange node, that's C, and then C has a path that goes toward a pink node, and C has a path that also goes, the orange also has a path toward a green node. And then if you start at the yellow, it has a path to the pink and the green. So now we can fill in. So from the orange, from C, there is a path to the pink, which is 12. And then from the orange, there's also a path to the green, which is 12. And then starting at the yellow, we see that there is a path from the yellow to the pink, and that goes through 6. And then from the yellow to the green also passes through a 6. And so if you look at it, the pink node is what we call A, the green node is what we call B. Of course, there's no connection between them, and then we can go back and fill our colors in all the way if you like to make it more apparent. And again, I find the colors, get your colored markers, I find that to be so much more easy to deal with when they get complicated. And so now if we look at the circuit, we see that any current that flows through this 12 ohm resistor must also flow through the 6. Any current that flows through this 12 ohm must also flow through that 6. So we can redraw the circuit one more time, and we have 12 in series with 6, which is going to be 18 ohms. And then we also have another 12 in series with 6. That's another 18 ohms. We can put our colors back on if you'd like. So this is the orange node, this is the C node, and then this is the yellow node, that is the D node. And we see these 2 resistors are in parallel because they have orange to yellow, so any voltage that appears across one is going to appear across the other, so they're in parallel. So there exists an equivalent resistor, which is the parallel combination of 18 and 18, and that would be 9 ohms. So I can replace the given circuit with a single 9 ohm resistor and I'll have the exact same behavior. So that's how we do resistor combinations. Let's look at a few things real quick. And let's look at combining voltage sources and current sources in series and parallel. And there's a couple interesting things, and it falls out pretty readily from what we already know, but maybe you haven't thought about it yet. And so if we have two voltage sources in series, is there an equivalent voltage source that we can come up with? And so what we can do is we're looking for a voltage V question mark. Of course, this has to be V question mark. So does the V question mark voltage exist? And we can find that very easily by writing KVL. So KVL minus 5 minus 7 plus V question mark must equal to 0. And if you solve for V question mark, you'll find that V question mark must be 12 volts. And so if I were to make this a 12 volt source, then this 12 volt source is equivalent to the series combination of 7 and 5. So when voltage sources are placed in series, you can simply just add them all up and that will be the equivalent voltage source. And this is what happens in your electronics. If you have a piece of electronics that has multiple batteries in it, typically if you look at them, the batteries are flip-flopped in their orientation when you install them in the battery compartment, and that's so if you look at the pieces of metal that are in there, they're putting those batteries in series to build up a larger, higher voltage. Let's take our voltage sources and put them in parallel. If we have two voltage sources that are in parallel, is there a possible voltage source which I could replace them with? And let's look at this and see. And so again, these are voltage sources, so let's write some KVL. All right, so is there a V question mark there? And so if we write KVL, we have minus 7, and then we go around down this way, and we'll see minus 7 plus 5, and we're back where we started from, equals 0. And this is negative 2 equals 0. What? Well, that's because what are you doing what is parallel? Parallel is, remember, two objects are in parallel if they have the exact same voltage across them. So if the 7 and the 5 are in the parallel, they have to have the same voltage or you have a conflict. We violated KVL in this case. So you cannot connect voltage sources in parallel. It's not possible. The only way you can connect two voltage sources in parallel is if they have the exact same voltage. If this were both 7 and 7, then that would work, and of course this would be 7. But we don't do that in practice because actually it's very, very hard to make two voltage sources with the exact same value. They always differ by a little bit. So let's look at current sources. We have two current sources in parallel. Is there a current source, I question mark, that exists that is equivalent to this? Well, this is the dual of what we just looked at, and of course in the previous examples we used KVL, so now we're going to use KCL. I can find a current that goes to the right at this location, which has to be this current right there if they're going to be equivalent, and we'll call this I question mark. And so we see I question mark by KCL has to be 5 milliamps plus 2 milliamps, and we get 7 milliamps. And so if this were a 7 milliamp source, then this single current source would have the same behavior as these two current sources in parallel. So we can combine those. And let's look at the fourth case, which is current sources in series. And you may have already got an inkling of how this is going to work out because of duality. Can I create a current source that has the same behavior as these two in series? And so what we do is we'll write KCL at this point right here, and we see that we have 2 milliamps entering, and then we have a negative 5 milliamps entering that direction, and that has to equal to 0 by KVL, and we see that this is what? Well, not possible again, because the definition of being in series is if these two elements are in series, they have the same current flowing through them, and if the current sources have different values, of course a current source always has whatever its number is flowing through it. This is not possible. The only way to put two current sources in series is for them to have the exact same value. Alright, so in this discussion we've seen how to combine series and parallel connected resistors and find equivalents, and then we've also considered the cases of series and parallel connected current and voltage sources. Alright, go back and work lots of examples. These are always great brain teasers, and we'll see lots of those, and it becomes very handy to take a bunch of resistors and combine it into a single resistor, because that way we only have one number to worry about. It makes our problems a little bit easier. All right, see you next time.